we're going to go 5.2b and 5.3. 5.2, I believe we ended, I can't remember exactly, I should have looked at the video a little bit, but it was, I'm going to start with the complement. And this is on the bottom of page 221. And it says, look, if A is an event, then the complement of A is the event that does not occur, okay? And the way we notate it is A, so if A is the event, then the complement, oh, let me move this a little bit to make it a little more easier for me to write.
We actually ended it mutually exclusive.
Which is perfect, because this is that next thing, right?
Okay.
Okay, good. So complement is A, and you write a little C up there. Now, I'm going to tell you, in other books, so if you want to get on YouTube and start looking at other, people like lecturing about complement, you're going to see this written 3 different ways. I think in a previous lecture, I wrote it with a bar above it. That's another way to write it. And there's some authors that use a little dash. Now, I'm going to try my hardest to stick to this notation because that's what your book uses, okay? But realize if you want to go and start looking up stuff and you see these symbols, it just means the complement, okay? It just means the complement. I'm going to give you, like, let's say give you a basic example. Let's say I look up the stats on our campus, and the probability of you being a freshman is 0.62, okay? The probability of you being a freshman is 0.62. Well, the complement of that would be not being a freshman, okay? So let's say we were on a 4-year campus. Kind of imagine it that way. We're on a 4-year campus. There's 62% of that campus is freshmen, which is a lot. So, but I want to know, well, what's the probability you're not a freshman? Well, the way we would notate that would be like this. So this just means the probability you're not a freshman. And what's nice, the easy way to find a complement, if you know the event, is it's just 1 minus the probability of the event occurring, okay? Which makes sense. If really 62%, right? 0.62 are freshmen, then 1 minus 0.62 are going to be not freshmen. So this winds up being, the probability of not being a freshman winds up being 0.38, okay? 0.38. And notice, these are the only 2 things that can happen. You could be a freshman or you cannot be a freshman, right? And both of these add up to 1, right? Because they're really, for this, not experiment, but for this example, that's the only 2 things that could happen, right? Ooh. It's the only 2 things that could happen. Like if we looked at, let's say, a deck of cards, we've kind of talked a little bit about deck of cards, right? If we look at a deck of cards and we want to know what's the probability we draw a king, right? We do 1 drawing. What's the probability we draw a king? Now, there's 4 kings in that 52 card deck. So 4 out of 52, right? 4 out of 52. Now I'm going to write it as a decimal just because that's what we do with probabilities. Typically, that's what we do. So 4 divided by 52. That winds up being, I'm going to round to 3 decimal places here, 0.077. Okay. But then let's say we're kind of trying to determine the probability of not being a king as well, if that mattered, okay, in some game we're going to play. So the probability of not being a king would be notated like this. And of course, we're going to have a much bigger chance of drawing not a king, right? It's all the other cards other than kings, right? Now, we would equationally find it as 1 minus the probability of being a king. And for us, we know that. Now I'm going to keep it in decimal. So it's 1 minus 0.077. So we end up with 0.923. Much higher chance of drawing something that's not a king if we had a deck of cards, right? Much higher chance. Okay. Questions about that? I know I've only got 2 of you guys in here now, and a lot of people are watching it later. but it's pretty straightforward. I mean, it's just if there's a chance of something happening, the complement is the chance of it not happening. Okay, it's the opposite. And it is important that we realize these complements always add up to 1. So again, if I wanted to write that notationally, like the only 2 options we have are drawing a king or not drawing a king, right? And they are going to always add up to 1. Whatever these 2 are, the 2 complements always add up to 1. Same thing here. 0.38 and 0.62, they always add up to 1, okay? Because they're really the only 2 things that can happen. Okay, I need your help here, Lori. Did I assign homework from 5.2?
Yes.
What did I assign?
I wrote it down here. All my millions of papers, and I wrote it down.
Yeah, I know it's been a few weeks.
I think it was 1 to. It was like 1 to 30.
Okay, I'm just going to start over. Let's say we in 5.2, I want you to do 1 through. I really want you to do a lot of these. 1 through 45 odd. Yeah, 1 through 45 odd. But I want you to make sure if you're not getting not if you're not getting it, but if you need extra work, do the evens. Okay, do the evens if you just feel like you need some extra practice. But 1 through 45
what you had assigned us was 1 through 42, and then 45 through 47.
I'm sorry,
5.1.
Yeah, I'm at 5.3. Good Lord, it's been a day.
Yeah, I'm looking at 5.
No. This is 5.2.
I'm looking at the wrong paper.
That's okay. Yeah, 5.2. It is 5.2, guys. I'm sorry. Man. 5.2, I want you to do 1 through 45 odd. Just do that. I don't think I signed homework from it.
No, I don't think you did. No.
Yeah, I don't think I did either.
Yeah.
And that's fine. So 1 through 45 odd and 5.2. And that way we can go into 5.3. 5.3 is going to take some time and really kind of understanding a few rules. 5.3 could be split up into 2 sections in all honesty. So let's look at 5.3 now. The first thing your book talks about in 5.3 is actually unconditional probability and then conditional probability. Excuse me. So conditional probability, we're going to start there. Conditional probabilities are in a few different ways. And it has to do with the probability of an event given another event, okay? So if I wanted like the probability of event A occurring given event B occurring, we would notate it this way. We should talk about notation real fast. So it would be A. Now we use an up and down line, a straight line there. That means given. So this means A given B, okay? A given B. Now I'm going to do a kind of a basic example here with this before we go over like the one in the book. And it's going to be, let's say, freshmen, sophomores. That's who we have on campus, right? And let's say we group them into 3 different groups. Let's see. Oh, let's say we poll them about who they're voting for. So we're going to go Republican, Democrat, and other. We'll use O for other. Okay. Republican, Democrat, and O for other. So, and I'm making this up, of course, off the top of my head. So we poll so many people, and it turns out that 25 freshmen. There's 25 freshmen that say they're gonna vote Republican, and there's, let's say, 20 that say they're gonna vote Democrat, and let's say 10 that say they're gonna vote other. Sophomores, let's say it's like, I'm going to try to keep these kind of nice. Let's say 18 say they're going to vote Republican, 22 say they're going to vote Democrat, and then let's say 5 said they're going to vote other. Okay, so we've got this group. Now I'm going to extend this out just to look at totals from each group. Okay, so if I add these up, so the people that just say they're going to vote Republican, let's see here. So 25 plus 18, that's 43, right? 43 told us they're going to vote Republican. Doesn't matter if they're freshman or sophomore. Democrats, 42. And then others, 15, right? And then on the other side, going to the right, how many freshmen did we have? Well, 25 plus 20 plus 10, that's 55, right? And then 18 plus 22 plus 5, that's 45. Holy cow, I did not mean to make these add up to 100. But notice, these are both going to add up to 100, right? Because this is everybody. The Republicans, Democrats, and other have to add up to the same thing as freshmen and sophomore. So this is our total. We actually interviewed 100 people total, right? 55 are freshmen, 45 were sophomore, 43 were Republican, 42 are Democrat, and 15 are other. And then we've got them grouped in here individually, okay? I'm going to use a different color pen now. I'm going to show you kind of how conditional probability works. Let's say I want to know what's the probability a student votes other given they are a sophomore. So the probability a student votes other given they're a sophomore. So this is a little different. If I want to use the chart here, look, I'm not going to look at freshmen for this example because we are saying that we are only looking at sophomores. That's the conditional part of the probability. The condition is we're only looking at sophomores. I am not worried about any of these freshmen now, okay? I'm not worried about the 55 freshmen that are there, okay? Does that make sense? So we're only looking at this line of sophomores now. And now look, the probability a student votes other, well, there were 5 sophomores that voted other. So now I'm going to write this out like you would write it as a statement. So votes other given they were a sophomore, okay? The probability that we voted other, we're in the other group, right? Given we're a sophomore. Now, this would actually be, there's 5 sophomores that are others, right? Out of 45 total sophomores. So if we do the math here, 5 divided by 45, 11.1%. Or, I shouldn't write it like that. 0.111. Because the probability a student votes given they are a sophomore is 0.111, okay? 0.11, 11.1%. That they are an other voter given that they are a sophomore, okay? That's where this is coming from. So if I wanted another one, let's say, I don't like this marker, it's too wide. Let me find a different marker. Ooh. Go through these and see, have I used all the good ones? I must have. Hold on. This one's not too bad. Okay, so let me kind of extend this down a little bit, but I'm going to keep the chart right there, okay? And I'm going to flip this. I'm going to say, well, what's the probability we are a sophomore given we vote, or I say vote, you know, this is from a survey, vote Republican. So this one's a little different. Now I'm going to introduce the actual formula, the algebraic formula for this. I should say the statistics formula. So the way this looks, and I'll introduce it with this example. Now, if we want to write this down, it's different. Now we're going to say the probability we're a sophomore given we voted Republican, right? The way this works is you look at the probability we're a sophomore and we're Republican over the probability we're Republican, okay? And the book goes over that. It's on page 227 if you want to see that the actual equation for it. But I mean, we're using the actual equation in an example. So now let's think about this. Now I'm going to just plug it into the equation. We'll see it's the same thing. Now look, first we need the probability because we're only looking at Republicans now, right? So now we're only looking at this column. We're not worried about these other three columns actually, because we're given that we're a Republican, right? Given we vote Republican. So none of these other columns matter. Now, we want the probability we're sophomore. Now, notice the numerator here on this probability, on this ratio, is we're a sophomore and we're Republican. Well, sophomore and Republican is right there, right? So 18. Divided by the probability that we're Republican. Well, I'm not using probabilities. I'm using total number counts, and that's fine. So 43 is the number count for Republicans, right? So think about this. Now I'm going to kind of show you how equationally it relates to what's actually happening. If I want to know the probability we're a sophomore given we're Republicans, so we're only looking at Republicans, right? And it turns out there's 18 sophomores that are Republicans. Well, there's 43 total Republicans, right? So 18 out of 43 would give us this probability, which if I put it in my calculator correctly, I've got 0.419. So about 41.9% are a sophomore given that they're Republican, okay? Given that they vote Republican, okay? Questions about this? That makes sense. Okay, I'm going to give you a few more and I want you to try them. So let's say I asked, what's the probability we are a Democrat given we're a freshman? And then what's the probability we are, let's say, how did I do that first? I'm going to flip the other one. What's the probability we're a sophomore given we're an other voter? Okay, so try those two real quick and see if we get the same answers.
Okay, for the Democrat freshman, I got 0.476.
Great, that's what Ivy got.
And the other one is 0.333.
Okay, let's see. I'm going to work them out. And I'm going to do them equationally, guys. So I'm going to straight up just say the probability of D and F over the probability of F, right? Well, the Democrat and freshman is 20. And the probability of being a freshman is 55. Is that how you got it?
No,
Uh-oh.
did it over 42.
Hold on. 20 divided by 55. Ooh, well, I'm glad we're going over this one. Okay. Think about it. The given statement here is that we're freshmen.
Oh, I went backwards. Gotcha.
Yeah. Do you see that, Ivy? So the given statement, hold on.
I see what I did.
It's Coulter. Yes, I see it now.
Oh, I'm sorry, Coulter, not Ivy. Yeah.
You're fine.
Yeah. So look, the freshman's the given statement. So that means we're going to use this total right here, right? And then we're trying to see, well, how many
Okay.
Democrats were freshmen, right? Or given that they were freshmen, what's the probability that they were a Democrat, right? And it turns out to be like 0.363. Okay, I want you to look at that last one now and see if you did the same thing.
Well, wouldn't that first one that you have, the sophomore and Republican, wouldn't that
Yep.
be 18 over 45 instead of over 43?
No, because the given is that the Republican. And so if the
Okay.
given's that the Republican, then that it's 18 over 43 because the given is that they're the Republican, right?
Okay.
The given here is freshman. So you got to go across to 55.
Freshman and Democrat,
But look, the given is that the Republican, right?
right?
So if the given that is a Republican, then they're one of these 43 people, right? Because the Republicans there's 43 people that are Republican.
Okay.
So that means
Oh,
it's
okay. Gotcha.
18 out of 43. Now, given down here is the freshman. So
It's
if they're
backwards.
freshmen,
Okay.
they're one of the 55, right? Oh, well, they're 18
Okay.
out of, wait. Whoa, oh, down here. Yeah, they're 20 out of that 55. So try that last one.
Okay. 0.364.
Yeah. Oh, yeah, it should be 4, shouldn't it? If we rounded that 3.
Yeah.
So try that last one.
Sophomore. Others. Out of 45.
So the last one is,
One,
the
one,
given
one.
is that they're the other, right? So out of these 15, well, they're sophomores, right? So they're 5 out of 15. So yeah, this would be 0.3 repeating, right? 0.333. Yeah, 0.333. Yeah, let's look at their example on this one, okay? And we'll work through it. So let me get some paper out. I have no room. I'm gonna steal their example straight out of the book. This is on the bottom of page 227. Coulter, do you have a book on you?
Yes, I do.
Perfect. And Lori, do you have your book right there?
Yes.
Good, because I don't want to write this down again. Okay, I don't want to write this whole thing. But if you're looking,
Okay.
it's on tape. It's table 5.5 on page 227. Okay,
Table.
and then it just gives it says table 5.5 presents the number of U.S. men and women in millions, 25 years old and older, who have obtained various levels of education. Right. So we've got the not a high school grad, some college, associates, bachelor's, and advanced. And then it's split on the other row by men and women, right? So let's see what they're going to ask. There's an A, B, and C. So A asked, what is the probability that a person is a man? So the probability we're a man, okay? Well, let's think about this. We're going to have to add up a lot of stuff here. We actually have to add up all of them to get the total, don't we? Because it doesn't say the total of people in this. The number of U.S. men and women. No, yeah. So we need the total. So we need to add up every cell here. And I guess, yeah, and the book adds up the total number of men and the total number of women, and then we can kind of get it from there. So if we look at the total number of men, I'm going to cheat a little bit because the book did it already. The total men equals 94.0. The total for females for is 101.0. So that means the total then, we got to add those two together. So 101 plus 94.0.
195.
95.
Yeah, you got 195? Yeah, 195. So this is our total. We need to know that, right? So if I want to know the probability of being male, well, it's just 94 out of 195, right? So the probability of male would be 94 out of 195. 94 divided by 195, boom, gives me 0.482. Okay, 0.482. They round to 1, so we'll do 1 for this example. They round to 4 decimal places. So in this example, the probability of being male is 44.821. Now I'm going to add an A1 here. I'm going to say, well, what's the probability of not being male? So female, right? But it's just a complement example. I'm throwing this in here. It's not in the book. We know that would be 1 minus the probability of being male. So 1 minus 0.4821. 1 minus 0.4821. So that becomes 0.5179. Okay. So the probability of being female, which in complement wise would be not male, right? And vice versa. If I want to know the probability of being male, you could say that's the probability of not being female. It winds up being 0.5179. So now let's go to B. B says, what is the probability that the person is a man with a bachelor's degree? So I'm going to say M for male, and we'll do B for bachelor's degree. Okay. What's the probability? Now, this isn't a given statement. It's not saying what's the probability you're a man given you have a bachelor's, right? It's just saying, hey, out of this chart, what's the probability, or out of the 195 people, 195 million people, what's the probability that you're a man and you hold a bachelor's? So if you go back to the chart, there's 17.5 million men that hold a bachelor's degree. Now, for this example, it's still out of the entire group, right? There's no given statement here. So it's just 17.5 divided by 195. So 0.0897, okay? 0.0897 is the probability that you are a male and you hold a bachelor's degree, okay? Not a big deal. C, I believe, is the complement statement, or not the complement, but the condition. It says, what is the probability that a person has a bachelor's degree given they're male? Okay, now I'm going to do this one equationally. This would mean the probability we're a bachelor, we have a bachelor's and we're male, which is right here, divided by the probability we're male. And we found those two things already, right? We know the probability of having a bachelor's in male, that's the same as male and bachelor's. It's a, what's the word? Commutative statement. So that's 0.0897 divided by the probability we're male. Well, we found that up here, right? 0.4821. So therefore it's 0.0897 divided by 0.4821. So that's going to be 0.1860. How do they get 0.1? They got 0.1862. That must have been because of rounding. Don't worry about that. Okay. So 0.1860. Because we did the same exact thing they did. 17.5. Yeah, it's just rounding. Okay. So that's a good example where we didn't use the chart per se. We just used probabilities to fill in the equation. Okay, we just use probabilities to fill in the equation. Okay, now look, we're going to use this now. So remember, the probability of A given B is the probability of A and B all over the probability of B, right? Now, there's a general multiplication rule that comes straight from this equation, and it's on the bottom of page 228. So let me get a fresh sheet of paper. It's on the bottom here. You writing that down, Lori? Okay, yeah, I'll give you a minute. Just give me a thumbs up when you're done. Okay, so again, okay, let me write this down. So if I want, got to have, I guess all of my Sharpies are kind of getting low. If I've got the probability of A given B, this is equal to the probability of A and B all over the probability of B. Well, you can really just use algebra and reword this. If I can multiply this to the other side, and we'd have the probability of B times the probability of A given B equals the probability of A and B. Okay? Now, that's the first example. And you can flip, if you flip these, you can say the same thing. Okay, I'm going to write this kind of how the book has it. A and B equals the probability of B times the probability of A given B. Now, if you do the inverse of this, where it's not A given B, but B given A, you would change that to A. So you can also say that A and B is equal to probability of A times the probability, you have to flip this, B given A, okay? And they call that the general multiplication rule. So let's follow their example, then we'll try one that doesn't just give us the example. It says, among those who apply for a particular job, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. Find the probability that an applicant is offered a job. This is on the top of page 229. So we've got to read through this and decide what's our given statement and what's our probability, okay? Now, if we look at this, so I'm going to go to the second sentence first. Among those interviewed, so that tells me the given is that they're interviewed. We're not looking at the non-interviewed people, right? So if we've got the probability given that they're interviewed, so among those interviewed, the probability of being offered the job. So the probability we're offered, given we're interviewed, is, they tell us what, 0.25? And then it says, the first sentence says, among those who apply for a particular job, the probability of being granted an interview is only 0.1, so 10%, right? So look, what this is kind of saying is, look, the probability you get an interview is 10%, right? But if you get an interview, the probability you get an offer is 0.25, which kind of makes sense. So they probably, what I'm kind of seeing is they're probably only bringing in 4 people for interviews, right? And one of you is going to get an offer. That's kind of what this kind of is telling me. But let's see. The question says, find the probability that an applicant is offered a job. Yeah, so offered. That's a weird way to put this. Yeah, so we've got an applicant who is, because you would actually say they, so an applicant that actually was offered and interviewed, right? So this would be the probability that they're interviewed times the probability they're offered given they're interviewed. So probability of I, we know 0.1 times the probability of 0.25, which turns out to be, is it 0.025? Yeah. Man, that's tough. It's a really slim chance that you get an offer, right, for this job. Yeah. Oh, I see what you're saying. So what's the probability an applicant is actually offered and interviewed, right? So I mean, like, you've got the probability that they're offered and they're interviewed is very slim, right? Very slim. Okay, so let's look at the example underneath it, but they don't work it out. So we're going to see if we can do this on our own. So this is the check your understanding. I assume you guys have that right underneath on page 229. And it talks about in a certain city, 70% of high school students graduate. You have that one?
Yeah, that would be one of the homework assignments.
Okay, well, let's do it. Let's do the
That's
homework.
how they do it.
Yeah. Oh, that's right. I forget. So let's try it though. In a certain city, 70% of high school students graduate. Of those who graduate, 40% attend college. Find the probability that a randomly selected high school student will attend college. So in a certain city, 70% of high school students graduate. I'm going to start there. So the probability that we graduate is 0.70, right? Now we got to read the second sentence, and it's really important how we read it. Of those who graduate. So that means the given is that they graduate. Right? The given is that they graduate because it's saying of those who graduate. 40% attend college. So the probability you attend college given you graduated is 0.40. Find the probability that a randomly selected high school student will attend college. So that means that they graduated and they went to college, right? And look, we just have to multiply these together. So it would be the probability that we graduated times the probability, oh, not I don't know where that came from. We attend college given we graduate. So 0.70 times 0.40. So 0.28. Is that the answer? Yeah, I told them the answer. So yes, that's the answer. 0.28. Questions? Now, okay, in a way, these aren't considered independent things that happen, right? I mean, if we graduate, the probability we attend college, there's a condition to it. The next thing we're going to talk about is independent conditions, or independence. Independence, I'm going to just read what the book says. In some cases, the occurrence of one event happening has no effect on the probability that another event occurs. For example, if a coin is tossed twice, the occurrence of a head on the first toss does not make it any more or less likely that a head will come up on the second toss. And we'll get to an illustration of this. So the condition, there's no real condition. It's not like, hey, if I flip a head on the first toss, what's the probability I flip a head on the second toss given I flipped a head on the first toss? Well, it doesn't matter because the probability of flipping a heads is 1/2 no matter what, okay? So even though there's consecutive events, those events don't change the outcomes as we go along, okay? As we go along. So the book says a fair coin is, this is the example. Fair coin is, what is the probability that the second toss is a head? Well, it's still just 1/2. It doesn't matter. Okay. The probability of any toss is going to be 1/2. Okay. The probability of any toss. And same thing for part B. What is the probability that the second toss is a head given that the first toss is a head? Doesn't matter because the first toss does not affect the second toss. So it's still just a 1/2. They use a lot of like math to explain this in their book, but I need you to realize since they're independent, it does not matter. Okay. And then let's, hold on. I got to determine blah, blah, blah. Look at the multiplication rule for independent events at the bottom of page 230. I'm kind of skipping ahead a little bit. Look, it says, look, if A and B are independent. Then if I want the probability of A and B, instead of it being this rule here, right, right here, that you have to say B times A given B and all that. If they're independent, it's a lot easier. It's just the probability of A times the probability of B, okay? It's just the probability of A times the probability of B. Because there's no chance of the first one having an effect on the second one. And I'm going to give you an example of an experiment where we, in one way we have independence and the next way we don't have independence, okay? So, and I'm going to use that deck of cards example, okay? So the first example, this is when we have independence. What's the probability of drawing a king twice? Now here's what's important. After we draw the first one, we put the king back in and shuffle it up, okay? So after first draw, we put king back in, okay? Put the card back in. Look, in this example, that second draw has no dependence on the first draw, okay? Because we're putting the card back in, right? Imagine I had a deck of cards and I shuffle them up and then I give them to you and you just draw that first card, right? And you tell me, oh, this first card's not a king or it is a king, doesn't matter. We know the probability of, now the way I would write this out would be I get a king the first time and I get a king the second time, okay? But you draw the first card, you look at it and you go, oh, it's a king or it's not a king, but then you give it back to me. I shuffle it up and then I give you the deck of cards again, okay? Well, this is purely independent. That second card you draw is completely independent of the first card, right? It doesn't matter. I mean, it doesn't matter. So this would be the probability of a king on the first draw times the probability of a king on the second draw. Well, we know the probability of a king is 4/52, right? Times the probability of getting, oh, that's a 2 right there. Probability of getting a king on the second draw is the exact same because we still have 52 cards, right? We put it back in. We put it back in. And I'm going to multiply these together. So you get 4 out of 52 times 4 out of 52. And you wind up with a really small chance. I mean, this makes sense that it would be a very, very small chance of 0.00. I'm going to go to I'm going to go to 6 decimal places, or 5. 0.00591. Really small chance that we end up drawing a king and then a king again. Okay? Independent. Dependent would be if you kept the card. Okay? What's the probability drawing a king and then you keeping the card and drawing another king? So it's going to look the same, right? Probability of a king and a king, right? But this one, once we do our first draw, which is still going to be 4 out of 52, right? I want you to catch up there. I'm going to talk. But that first draw would still be 4 out of 52 because I'm shuffling a deck. I give you the deck of cards and I tell you to draw. You draw that card. Hey, the probability we got a king is 4 out of 52, right? No matter what, because I haven't done anything. But now you're keeping that card. So it changes things up, right? It's saying, hey, the probability now we get a second king, there's not 4 kings left in the deck, right? There's only 3 kings left in the deck because you drew one already.
So that'd
So
be
that would-
3 over 51.
Exactly, 3 over 51. So this changes given what happens on the first draw, right? This changes given what happens on the first draw. So let me clear this up. 4 out of 52 times 3 out of 51. And we get 0.00452. Okay. Yeah, and your book goes over this. It's called sampling with replacement and sampling without replacement. You can go over it. Those are examples. This is examples of that. So I'll let you read over that in the book when you get there. Okay. Yeah. So the last thing your book talks about in 5.3 is the at least once occurrence. And man, this is just purely a, it's more like understanding the English of the math problems, okay? It's on the bottom of page 233. And it starts saying, sometimes we need to find the probability that an event occurs at least once. In several independent trials, we can calculate such probabilities by finding the probability of the complement and subtracting it from 1. So let's think, oh gosh, I might just, yeah. Okay, cool, yeah. They do a good example with dice being tossed, or I'm sorry, with not dice, coins being flipped. It says a fair coin is tossed 5 times. Now I'm going to write out everything that can happen with a fair coin tossing 5 times. Or what is the probability that it comes up heads? Oh, no, I'm not, because that would take it's a lot. Okay, I'm going to start down this path. A fair coin is tossed 5 times. What is the probability that it comes up heads at least once? Now I'm going to start trying to write out everything that can happen if I toss a coin 5 times. Think about this. We could get all heads. We could get 1 tail. Now, if we do that, though, there's a lot of different ways to get 1 tail, right? We could get it on the last toss. We get it on the 4th toss.
The first one, you need another H.
The 3rd toss, that's my other H right there.
No, the first one. There you go.
And then we get on the 3rd toss. We could get it on the 2nd toss, right? We could get it on the 1st toss. We could get we could get 2 tails, right? So head, 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 tail, tail. You see where, I mean, like this is going to go for a long time, right? If we did it this way. So it's a little easier when we have the probability of an event occurring at least once, because then we can do the complement of it. So let's look on the next page. It says, look, the tosses of a coin are independent. Since the outcome of a toss is not affected by the outcome of other tosses, the complement of coming up heads at least once is coming up tails all 5 times, okay? So the probability of coming up heads at least once equals 1 minus the probability, and I'm just writing this how the book does. It doesn't come heads up, doesn't come up heads at all, right? So the probability that it comes up heads at least once equals 1 minus the probability it doesn't come up heads at all, which we know. So the probability we're looking for, I'm going to say this is I'm just gonna say at least once so I don't have to write it all out. Would be 1 minus the probability it doesn't come up heads at all. Well, the probability it doesn't come up heads at all is 5 tails, right? This will be a lot easier to calculate because we know each one of those flips is independent. So because each one of those flips is independent, the first one doesn't depend on the second one, right? This is just probability of tails times the probability of tails times the probability of tails times the probability of tails. You get the rift here. I ran out of room. I can write it like this. The probability of tails raised to the 5th power, right? Because it happens 5 times. We know the probability of tails is just 1/2 raised to the 5th power. So 2 to the 5th is 32. So this is 1/32. This winds up being, I'm going to steal it from the book. Oh, it says it's 31 out of 32. Ugh. I'm going to use decimals because I want to know. It helps me out more. 31 divided by 32. 0.96875. Okay. Which kind of makes sense. Look, the probability it comes up tails at least once would be extremely high, right? I mean, it could come up tails once, it can come up tails twice, 3, 4, or 5 times. But it's really hard to calculate. You have to like add all those times up together, right? Or you can just say, oh, it's 1 minus the probability it doesn't happen, right? So and really what we're using is the complement here, right? So the probability at least once would be the 1 minus the probability of not at least once, right? So it's all tails. It's really the complement rule, which is kind of neat. Okay. Yes. Okay, good. I need you to go over 5.3 before I can get to 5.4. And I think 5.4 is the last section before chapter 6. Yeah, it is good. So for homework, it does start throughout the chapter, your book. Example 1 is on page 228. So I want you to do 1 through, we did 2 already. Yes, good. There's going to be a lot in this one, but it's not going to take that much time once you kind of see what's going on. And I hope you kind of come back with questions. If something doesn't make sense, if you're getting the wrong answer, especially with that conditional probability, you guys saw both of you got the same wrong answer, right, on that one question. So it's very normal to not grasp these at first. Very, very, very normal. But unless you do the homework, you're not going to know what you don't know. So I want you to do 1 through 57 odd. And it starts on like page, this is section 5.3. But it starts on page like 228 maybe. Yeah, 228, and then the bulk of it goes over to page 235. That's where it really starts. Okay, so I'm going to end here. I know I'm ending a little early, but it's because I don't want to go into 5.4 yet before